All right. Generally speaking, a Taylor series looks like the following. We could start it maybe at 0, although that part's really not important. But it may look something like c sub k x minus a to the k. And then when a equals 0, we call it a Maclaurin series. I don't know the history so much of this, but I believe that Maclaurin probably came up with it first for just x to the k, and then Taylor maybe came along and gave a little more of a general framework for it. But we already know how to do Taylor polynomials. A Taylor polynomial those are the ones that went p sub n of x equals the sum k equals 0 to n, and then you had f, the kth derivative evaluated at a over k factorial times x minus a to the k. Those are how we constructed the Taylor polynomials. We were simply going to then extend it, so allow n to go to infinity and get a Taylor series. About a. And those things look like some. It's the same thing. I'm just going to change the n to an infinity. All the derivatives are evaluated at a over k factorial times x minus a to the k. So basically, I'm just going to redo some of the stuff we did in determining Taylor polynomials and allowing this to go on. Now remember, this function f, in what we're going to do, our functions we're going to deal with are infinitely differentiable. That means I'm able to find a derivative for all values of k. I'm also going to make an assumption that there is a single interval about a, maybe an open interval, better yet, about a, in which all of these derivatives exist. So with that in mind, you'll see what I'm talking about. This is not as bad of a suggestion as it may seem. Let's start with compute the Taylor series for f of x equals sine of x about a equals 0. So really, this is a Maclaurin series. But what do we do? First of all, the function itself, we evaluate it at a. F of 0 is a sine of 0, and we know that that is 0. Now we start taking derivatives. F prime of x equals cosine of x, and so f prime of 0 is cosine of 0, which equals 1. And then f double prime of x, this time will equal negative sine of x. And then f double prime of 0 equals negative sine of 0, which is still 0. And f triple prime of x equals negative cosine of x. And f triple prime of 0 equals negative cosine of 0, which is equal to negative 1. And then by the time I get to the fourth derivative, I am back to the original sine of x. So we can see how it's going to go here. Our coefficients are going to go like this. My first coefficient will be 0, then I'll go 1, 0, negative 1, 0. And it just will repeat from then on. So then you'll have a 1, 0, negative 1. And let's take a look. I think writing out a few terms is better than trying to muscle your way into the series form summation right off the bat. So let's see what it's supposed to be. Sine of x is supposed to equal all this business. And what do? We start with, well, actually, I'll tell you what. Let me do it this way. In our general format, f of x is going to be f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared, but this one you have to divide by 2 factorial, plus f triple prime of a over 3 factorial times x minus a cubed. And of course that goes on forever. So I'll try to mimic that. My f here is of course sine of x. So I'll start here. I'll have and a is 0. So I'll have f of 0 was 0. Then I'll have plus 1 times x minus 0. And then the second derivative of 0 was 0, so I'll put that there. Plus 0 times x minus 0 squared plus the third derivative, that turned out to be a negative 1. Oh, don't forget this. I often seem to be doing that lately. Then we have, since it's a negative 1 there, I'll have negative 1 over 3 factorial times x minus 0 to the third. And then it'll repeat again. So I'll have 0 over 4 factorial times x minus 0 to the fourth. I'll put one, maybe a couple more here. 0 over 4 factorial times x minus 0 to the fourth. And then I think it'll go negative again, no, positive again. And I'll stop right there. If you look at the terms that we have here, the 0th term, that's better to think of it as the 0th term, is 0. But then the first term has a 1x. The second term has a 0, but the third term is negative 1 over 3 factorial. So let me write this out. I'm just going to write the non-zero stuff. So I'll have x, all this is just x, and I'll have minus x, I don't need parentheses around it. I did that to show, but it's just x cubed. X cubed over 3 factorial plus x to the 5th over 5 factorial. And you can probably see what's going to be going on right now. Then I'll get minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Just write out enough terms so that you feel comfortable with what the series will look like. And then this will go on and on. So if I want to write it as a series, I'm going to think of that to the first power, and it's only going to have odd powers. The way you make only odd powers occur is to do something like this, 2k plus 1. Since I want to start at 1, that means my k had better start at 0, because when k is 0, I got x to the 1. So I've got the powers handled. Now these denominators are the exact same, except for the factorial, as the exponent. So like whatever I have in the exponent, I have down there as well. So I can put, I think, yeah, why not? Put 2k plus 1 factorial. And then it's alternating. Every other term is negative, where this one here is a positive. So I could do something like negative 1 to the k, and let's see if that works. All right, when k is equal to 0, I'll get 1 x over 1. So I'll get the first term. You only need to do this for a few terms to know if you're going to be right or not. Then when k is 1, I'll have negative 1 to the 1, so it'll be negative. But then I'll have x to the third over 3 factorial. That matches this. When k is 2, I'll have a positive. The term will be positive, but then when k is 2, I'll have x to the 5 over 5 factorial. So this is going to work. So this guy right here is my Taylor series, and this represents sine of x when x is around 0. What is the interval of convergence? And of course, since I have a factorial, it's probably better to use the ratio test than to use the root test. So for that, we'll look at the quotients of a term and its previous term. Now, once you do the absolute values of this, you can ignore the minus sign because, or whatever this thing is going to be, because it's going to squash that anyways. So all I have to do is work with these things. So I'll have x, and instead of a k, I'll replace it with k plus 1. And likewise in the denominator, I'll get 2 times k plus 1 factorial. And that's supposed to be divided by the kth term, which is x to the 2k plus 1 divided by 2k plus 1 factorial. And remember, this is supposed to come out to be less than 1. I'll do the typical flipping around of stuff. I will get, and also I'll simplify here. This will be x to the 2k plus 3 that means I'll also have a 2k plus 3 factorial, and then I'll multiply by 2k plus 1 factorial divided by x to the 2k plus 1. So I'll do some canceling here. When I cancel out the x to the 2k plus 1, that will leave me with just x squared in the numerator. And then when I cancel out 2k plus 1 factorial with the 2k plus 3 factorial, what it will leave in its wake is 2k plus 3 times 2k plus 2. Because from that point on, it would have been the factorial had it been there. Now, notice this. I have k's, but they're positive. X squared can't be negative, so I can drop these absolute values completely. So I'll have x squared all over 2k plus 3 times 2k plus 2. And that's supposed to come out to be less than 1. Now, x is not involved in the limit, so I'm actually going to bring it out front. So I'll have x squared times the limit as k goes to infinity, 1 over 2k plus 3 times 2k plus 1, and that's supposed to come out to be less than 1. But this limit is 0 because I'm going to have 4k squared. It doesn't matter. The variable's in the denominator. The thing's going to go to 0 if the top is just a constant. So I'll get x squared times 0 is less than 1, and that's true. This is true for every value of x. So the interval of convergence equals negative infinity to infinity. And remember, the radius of convergence is infinity. So this means that sine of x equals the sum, k equals 0 to infinity, negative 1 to the k, times x to the 2k plus 1, all over 2k plus 1 factorial for all x. So I don't have to worry about being near anything. This works for every real number x. This is one of those infinite series that it's worth memorizing and just having it handy. If I ever see a series like this or anything remotely like it, this is the first thing I think of. Notice that these powers are all odd. Sine of x is known to be an odd function. There's no mistaking that this matches. If you do the same thing for cosine, you're going to get only even powers. And guess what? Cosine is an even function. If you do the same kind of thing for tangent, you'll get only odd powers. And guess what? Tangent's an odd function. So these make it quite explicit what is even and what is odd. I don't know if I've actually made an example yet. The first thing was an example, so I'm going to example 2 now. I want to estimate sine of 1 to 4 decimal places using the series we found. And you might find it easier if you wrote it out, like sine of 1 is supposed to equal, remember when k equals 0, we get x, just x, so it's going to equal 1. And then when k is 1, we're going to get negative 1 over 3 factorial, because that'll be 1 to the 3rd. And then I'll have plus 1 to the 5th over 5 factorial, minus 1 over 7 factorial, 1 over 9 factorial, and this goes on forever. So what I'm going to do is use your calculator, or at least kind of calculator I think most of you have, and that's one of the TIs, and just calculate until I see the decimals start to line up to the 4th decimal place. So let me push the calculator to the side, and I'll start with 1 minus 1 divided by 3. Now if you're looking for the factorial on your calculator, press Math, go to PRB, Probability, and choose number 4. Now here's the real time saver. The next term I want to add is 1 over 5 factorial, so I don't have to type it all again. I can simply hit the plus key, and it'll take my previous answer, and now I can add to it. So I can go 1 divided by 5 math. You can scooch to the right to get to PRB, or if you hit the left, it'll wrap around, and then choose item number 4, and then enter. Now what I have is essentially 1 decimal place of accuracy, because the previous answer and this answer agree in 1 decimal place. Although, maybe it's getting close to 2, so I'm going to do some more terms. So I'm going to go minus 1 divided by 7, and then I'll go and do my factorial. All right, so it looks like now I have 0.84, 0.84, kind of locked in. So I think I got 2 decimal places right now. Let me add then 1 over 9 factorial. So I may have 3 decimals now, maybe even close to 4. 8414, 8414, although the rounding, these both round it to 8415. So I feel all right here. The next one after 1 over 9 would have been 1 over 11 factorial. So let me go ahead and subtract 1 divided by 11 factorial. So I'll go math, PRB, 4. Now, to me, I have enough decimal places. 0.8415. So let me write that down. That is because the next decimal, it was 47, so I rounded to 4 decimal places. So that's how you can tell. You can even really hammer it home if you simply have your calculator try to do sine of 1. But doing this kind of defeats the purpose of having the power series, I guess. But let's write it and see. And you can see that our answer up to the 11th, so what was that, the 1, 2, 3, 4, 5, the 6th term, by the time I got to the 6th term, look, they're in agreement to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. And they're working on the 10th. So it's pretty quick. right, for another one, I would say when you get the chance, whenever you get a chance, and you see something like this, f of x equals 1 over 1 plus 2x, don't be afraid to use the series as we've already used before. For example, we know that 1 over 1 minus x equals the sum k equals 0 to infinity, and we would have x to the k. Well, this is quite similar to it. This one here, if I thought of it as 1 over 1 minus negative 2x, then I can use the same formula. K equals 0 to infinity, and I'll have negative 2x to the k. Or I might write it as negative 1 to the k. It's usually a good idea. I found it to be a good idea to strip away the sign as not being a part of the other part. The reason why I'm saying this is this doesn't tell you anything about the magnitude of things. It's the non-1 stuff that tell you about the magnitude. And here I'll write this part as 2 to the k, x to the k. And to determine what the radius of convergence and the interval of convergence, we basically already have that, because this here is true for the absolute value of x less than 1. Let me move that out of my way for a second. So I'm using that as my model. And it didn't even matter if there was a plus there. It was the same kind of a thing. Like, here's more like our series even. Well, then, all I got to do is look at this part of it and know that the absolute value of 2x has to be less than 1. Well, that 2 is not part of the absolute value necessarily, and then I can divide by 2. So if you want the interval of convergence, you can solve this and you'll get negative 1/2 is less than x is less than 1/2. The only thing, though, is you got to check these endpoints to see if they're part of it. So I may put a less than or equal to in here. So let me check them out. Here's my series. So first we'll check out the endpoint. X equals negative 1/2. And I'll put it back in that series. So let me grab this guy. Alright, so if I put in the negative 1, then negative 1 to the k and this have the same sign. So I can just take that out and forget about there. It's always positive now. So when I put these two together, it's simply going to give me a series of 1s, and that's infinity. So it's not going to work at negative 1/2. You know it's not going to work at 1 either. I mean 1/2, because we've already done this before. When x equals 1/2, we are going to get and now this one will simply end up, the 1/2 and the 2 will cancel, and then you'll get this alternating business, and that doesn't converge either. So I did have the interval of convergence already done. And r is 1/2. The radius is 1/2. So you see, there's nothing different than I was doing with Taylor polynomials. Absolutely nothing. These tests you've seen before, so nothing should surprise you. I keep saying Taylor, but it's technically Maclaurin series. How about the Maclaurin series for hyperbolic cosine? So in this situation, let's start as usual. F of 0 is cosh of 0, and that equals 1. This is the perhaps one of the best of all the series there are. Check this out. F prime of x equals hyperbolic sine of x. And there's no negative in front of it. So when I do f prime of 0, that's hyperbolic sine of 0, and that's equal to 0. Then when I take the next derivative, prime prime, that equals cosh again. And of course, cosh of 0 equals 1. So you can see where this is going. It alternates 1, 0, 1, 0, 1, 0. So my series will look like then, my 0th term, so cosh of x should equal, so I'll have 1 plus, and then f prime of 0 is 0, so you'll have 0, f prime was times x to the 1 power, 1 times x squared, but that's over 2 factorial, then 0 times x cubed over 3 factorial, and you can see the pattern developing there. I'm going to end up with 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. And here's a series that only consists of even powers. And so the easiest way to write this is a sum k equals 0 to infinity, and we can just do x to the 2k over 2k factorial. Make sure you put the parentheses around it. If you don't, I'll think when I look at it that you're just talking about 2 times k factorial, which is not the same as 2k factorial. Now, some of the things here that we need to check are what is the interval of convergence? So we do the same thing as we always have. The ratio test is preferred here because it's not just powers. So the ratio test will give me the limit as k goes to infinity, absolute value of x to the 2k, but k is replaced with k plus 1. And then then I have the kth term. I'll have 2k factorial all over x to the 2k. Now, all these things being to even powers means nothing's going to be negative, so I can draw up my absolute values. And then here I'm going to have x to the 2k plus 2 all over 2k plus 2 factorial times, and I'll have 2k factorial all over x to the 2k, and that's supposed to end up being less than 1. I can take out x to the 2k and leave just x squared, and then the 2k and the 2k plus 2, I can cancel these things, and what I'll be left with down there is 2k plus 2 times 2k plus 1. And then I can take the x squared out front, and we've pretty much done this game when I was doing the series for sine. I think it came up to almost something like that, almost identical to this. This part once again is 0, but this is true for all x. So the interval of convergence is negative infinity to infinity. So I should write this is true for all x. Estimate cosh of 2 to 4 decimal places. Using the series above. So cosh 2, let me go back to the series. What was that? Right here. So I'll write it in long form like this. So I'll get a 1 plus 2 squared over 2 factorial plus 2 to the 4th over 4 factorial plus 2 to the 6th. So let's go ahead and throw all those in. So I'll have 1 plus 2 squared over 2 factorial plus 2 to the 4th all over 4 factorial. 2 to the 6th over 6 factorial. 2 to the 8th over 8 factorial. Oh, we'll see how far I have to go with this. Once again, I'm going to pull up your calculator and let it do this kind of work for me. So I'll have 4 over 2 factorial. I don't intend to do a lot of computation in my head. I'll plan on letting the calculator do most of this work for me. Next one was 2 to the 4th over 4 factorial. Make sure you come down from there by clicking that before you proceed. Whenever you see this kind of an error syntax, hit the go to and it will almost tell you where you made your mistake at. And I didn't have anything in front of the factorial, so I need to have a 4 in front of there. Okay, now let me add the next term, the 2 to the 6th over 6 factorial. Right now, I don't even have 1 decimal place locked in quite yet. So I'm going to go 2 to the 8th over 8 factorial. Okay. It looks like I got about 1 decimal place lined up right now. So I'll keep going. Remember, these are only even powers, so I'll have 2 to the 10th divided by 10 factorial. So 3.76, 2 places feels all right. Let me then add 2 to the 12th over 12 factorial. Three, 3762. Oh, it looks like I may even have this next place may be a 2. So 4 decimal places, so 3.7622 is what I'm going to think. I'm going to add a couple more just to be on the safe side. So I'm going to 2 to the 14th. And I'll divide by 14 factorial. Three, 376295. It's looking pretty good. So I would say 37622, rounding to 4 decimal places. Let me add one more term just to see how this is going to work out. So I'll do 2 to the 16 divided by 16 factorial. Yeah, now I really feel good about it. So my thing is approximately 3.7622. That's the 4 decimal places. And if you want to check it on your calculator, if you look along your keyboard, you will not find any of the hyperbolic functions. If you want to find it, I'm not sure where they keep it at other than in this one spot. If you hit second and go above the 0, it's a catalog of all the known functions. Now, if you look up here as a little a, it means it's prepared for you to strike a key to tell what letter to start with. So if I go to where it says PRG, notice the letter C is above that. It'll take me to all the things that begin with the letter C. And now I will scroll down and see if I can find my cosh. Cosine, cos inverse, cosh, there it is. Hit enter. Put a 2. If this is the only thing you're doing on this line, you don't even have to complete the parenthesis for it to tell you. And you can see that, in fact, I have agreed with so many 9 decimal places when I got to that 16th term. Find the Taylor series for e to the x about a equal natural log of 2. And so the procedure you follow when there is a non-zero a is no different from the other ones. You're going to simply write e to the x equal to the sum from k equals 0 to infinity, and you're going to do just like you did before, f to the k evaluated at a all over k factorial times x minus a to the k. That's all you're going to be doing. Your series, instead, the derivatives will be evaluated at a, and you'll just tack this on. It's basically just a shifting, if you will, to the right by a units. All right, so let's go ahead and like our normal stuff. By the way, I mentioned an f here, but I didn't here. E to the x will be our f of x, so that I can write this kind of stuff and not confuse you. Let's start with f of ln2 equals e to the natural log of 2, and then e, of course, cancels with the natural logarithm to give you 2. This is the, by the way, if you want to think of this, this is like the 0th derivative, just evaluating the function itself. Then f prime of x equals e to the x. Well, nothing could be simpler than this. F prime of ln of 2 equals e to the ln of 2 equals 2. If you ever get assigned a problem like this involving e to the x, celebrate. It's so simple that you can do it without much thought at all. Every derivative is the same. I don't even know why I'm writing still. Pretty simple then, that e to the x is going to equal, every single derivative evaluated on 2 was 2. So I'm going to have 2 over k factorial times x minus ln of 2 to the k equals 0 to infinity. Compute the Maclaurin series. So because this is no more difficult than the other one, you'll see that doing Maclaurin is no more or less general than these kind of things. I do urge you this. I didn't do it, and I didn't determine the interval of convergence. I'll just specify it. You can check it out for yourself. The interval of convergence for e to the x is negative infinity to infinity, just like the other ones I've done, some of the other ones I've done so far. All right, let's compute the Maclaurin series for f of x equals arctangent of x. I think we did it, but I want to do it by hand. I did it, I think, in a roundabout way last time. But let's take a look. F of 0 equals 0. and then f prime of x equals 1 over 1 plus x squared. So f prime of 0 will equal 1. And then the derivatives, they get messy at this point on. F double prime of x equals, now I think of this as being 1 plus x squared to the negative 1. It makes subsequent derivatives easier. So I get negative times 1 plus x squared to the negative 2 times 2x. And then when I plugged in 0 there, that becomes 0 because of the 2x. And then we do it again. And I did this one before. I think we have found that this series ended up being sum k equals 0 to infinity. And this is the one that went 1 minus 1/2 plus 1/3. Or was it? No, it was just the odd terms because of these. It was just the odd terms. Arctangent is an odd function, so that should make sense. Yeah, that's the one it was. And then what you can do is my next example will use this as a building block. So when I do example 8, compute the Maclaurin series, for f of x equals x arctangent of x squared, I can use this for my arctangent. That means wherever I see an x, I'm going to change it to an x squared. So, and this x that's out front, I'm just going to let it hang for a minute until I get through with the rest of it. So k equals 0 to infinity. We have the negative 1 to the k. That doesn't change with whatever x is. But now instead of an x here, I'm going to put an x squared there. And then I'll get a 2k plus 1 all over 2k plus 1. Let me simplify a little bit here. When I take and raise x squared to the 2k plus 1, you multiply these exponents, and you get x times the sum, k equals 0 to infinity, negative 1 to the k, and then I'll have x to the 4k plus 2, all over 2k plus 1. This is fine as an answer, but if you feel like you should have to suck that x in there and make it part of the series so that there's nothing out here, it's fine with me as well. If I bring the x in, remember it's x to the 1 power, so this will become x to the 4k plus 3. And so my final answer could be k equals 0 to infinity, negative 1 to the k, x to the 4k plus 3, all over 2k plus 1. The binomial series takes its inspiration from the binomial theorem. Here we're going to take a look at a function f of x equals 1 plus x to the p. Now, if p is any kind of a natural number, there's a formula for how you write this thing out, and it's known as the binomial theorem. I think what I'm going to do is let's make the following assumptions. P is not equal to 0. That really, p equal to 0 doesn't really do much for us. So if p is not equal to 0, let me see what we can do with this thing and actually get a series without actually knowing what p is, and then I'll deal with it. Except I don't want, let's just say this, p is not a natural number in this example. The reason why I'm doing that is because I want to take an infinite number of derivatives, and if p is a natural number, by the time you take the p plus first derivative, it will have zeroed itself out. It's just a polynomial anyways. So those have been covered in like college algebra courses that you've had before this one. So instead, I'll deal with other p's where I can take derivatives forever. So let's start doing that and see what happens. We'll start first with f of 0. I'm going to do a Maclaurin series about x equal to 0. So f of 0 will be 1 plus 0 to the p, and that, of course, will equal 1. And I'll start taking my other derivatives. F prime of x equals, bring this p down, 1 plus x to the p minus 1. Of course, the derivative of 1 plus x is 1, so I don't have to worry about that. And then f prime of 0 is going to equal, think of x equals 0, so this will be 1 times p. And then f prime prime of x equals p times p minus 1 times 1 plus x to the p minus 2. And then when I plug that in, I'm going to get p times p minus 1. Please do not feel the urge to multiply this out. You'll miss all of the important patterns that we'll be needing to use to make the series. F prime prime of x equals p times p minus 1 times p minus 2, 1 plus x to the p minus 3. Then f triple prime of 0 equals p times p minus 1 times p minus 2. Of course, if p were a whole number eventually, we're dealing with something referred to as the factorial, p factorial, if I got all the way down to 1. But if p is not a natural number, and p is not 0 because that doesn't do anything, that means that eventually these are going to delve into negative exponents. But hopefully you can sort of see the way this is going to work. If I do, here, look at where it ended here. This is the third derivative, but that ended at a 2. So if I continue here, I think the pattern that I'm looking for looks like this. So I'm going to have p times p minus 1 times p minus 2, and that's going to continue on until I get to p minus k. Here, remember, this is 1. This 2 is 1 less than the 3, so I'm going to get a k minus 1 there. And then I'm going to have 1 plus x, and this here, the next one here, matched with this. So if I have a k here, this is p minus k here. And you may think of writing it like this, p times p minus 1 times p minus 2 until you get to p minus k plus 1 times 1 plus x to the p minus k. Hopefully this is enough to see what it's going to look like when I do 1 plus x to the p as an infinite series. I had a 1 to start it off. That was like the 0th term. But then I started having these a p times p minus 1. Try as I might, I can't quite write just a series. I'm going to separate this term, 1 plus, the rest of the series, because it just doesn't fit in a format that looks like this. It's just too soon. But after 1, this is fine. Then I can start k equals 1 to infinity. Then I'll have p times p minus 1 times p minus 2 dot 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 p minus k plus 1, and that is that's where these numbers were here. I'm sorry, that's these numbers. F to the k would have that, and this was a Maclaurin series, so I'm going to have x to the k, and this is going to be over k factorial. These are a lot easier than they look. They're really bad. This looks horrid for a series, a binomial series, but it looks a lot better than this in real examples. how do I figure out the interval of convergence? Well, I would take this stuff here, but I would do the k plus 1. So let's go ahead and do that. The limit. I think since I have all this stuff here, I'm not going to do the root test. I'm going to do the ratio test. The limit as k goes to infinity. And so I'll have this, but I'll have one more term than that. So what I'll have is p times p minus 1 dot 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 times p minus k plus 1. That's the kth term, right? These are like growing, if you will. That was a k minus 1, then p. Then the next term would be p minus k, and that would be to the x to the k plus 1. And then down here I've got k plus 1 factorial. And then, as we usually do, I'm going to have this times k factorial all over. And then I'll have this stuff, but I'll only go up to here. So I'll go p times p minus 1 dot 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 p minus k plus 1, like so. And then I'll get an x to the k down here. And remember, that all has to be less than 1. This isn't as bad as it looks because all of this stuff will go away, like that. Most of the x's will go away, like so. Most of the k's will go away even, like so. And we will be left with the absolute value of x. So I will have the limit as k goes to infinity, the absolute value of p minus k times x all over k plus 1. It's supposed to be less than 1. I'll factor the absolute value of x out front, so I get the absolute value of x times the limit as k goes to infinity. And over here I will still have p minus k all over k plus 1. Notice the k is, this piece up here is eventually going to be negative, so I can't drop these. That's less than 1. Now, this limit is negative 1. The leading coefficients, p is just a constant, so I have negative 1 over 1. I'll get the absolute value of x times 1 is less than 1, or negative 1 is less than x is less than 1. Now, I don't know how much of this I want to write, but there are complications with the endpoints to no end. For example, if p is a natural number, then the interval of convergence is negative infinity to infinity. Well, we assume that wasn't the case anyways, but then we have all sorts of other complications to this. If p is less than or equal to negative 1, the I of c equals negative 1 to 1. If negative 1 is less than p is less than 0, so if p is positive, but p is not a natural number, then the I of c equals negative 1 to 1, but including. And I think I've taken care of all the cases. Your best bet, I think, for almost all circumstances is going to be dealing with it like that. So, but just be aware of these. There's a lot of complications to it. It's not fun to go through each of these and try to verify these things, so I'm not going to bother with it. You can look through your book. I'm not even sure they do it, to be honest. Or they might do it in exercises or something. Anyways, let's test how accurate this thing is, and let's use example 9. Let's use the binomial series to estimate the square root of 1.2. And the way you need to think of it is this way. The square root of 1.2 equals 1 plus 0.2. That's to the 1/2 power. So this guy right here is your x, and that up there is your p. So now you're ready to use the formula. And I don't even recommend the series notation for this. It works like this. You keep doing p, then times p minus 1, then times p minus 2, then p minus 3, etc. The way this looks is the following. It looks like 1 plus, and then we do p. X would be, well, let me actually tell you what. Let me do this first. Let's go ahead and use that as the setup. My p is 1/2, and my x, if we want to keep this all in fractions, you can write it as a decimal, I really don't care, or as a fraction. If I usually ask a question like this on an exam, you'll have to use this to get your answer. If you just use your calculator, you'll get 0 credit. So let me go ahead and write my numbers in then. 1 plus, I guess what I'll do is use p equals 1/2, and my x will be 1/5. So 0.2 equals 1/5. I'll use that, so I won't mix decimals and fractions. And then the next one we're going to have is 1/2. Then I'll have 1/2 minus 1 over 2 factorial times 1/5 squared. And then I'll have plus 1/2, 1/2 minus 1, 1/2 minus 2, all over 3 factorial, times 1/5 cubed. And then I think by now, I'll do one more just so I can see, just so you can see the format. 1/2 minus 1, 1/2 minus 2, 1/2 minus 3, all over 4 factorial times 1/5 to the 4th. And that goes on and on and on. And to make matters simple, I get 1 plus 1/10 minus 1 over 200. So there's the 1, there's the 1/10. This ends up being 1 over 25. That'll be the 100, and then another 2 will give you the 200. Then I get plus 1 over 2,000 minus, and go ahead and use that as your estimate. And then you've seen what you do. Go and plug these in until you get so many decimals of accuracy. And just keep going until you've reached, I don't know, don't even remember if I didn't even tell you how much accuracy you used. On a test, of course, I will tell you how much, or I might even tell you how many terms of the series to do.